Here we're going to talk about refrigeration. And refrigeration, do some calculations and look at a real versus an ideal refrigeration cycle and look at scale up of a refrigeration cycle. Refrigeration is moving heat from a low temperature to a high temperature. That's moving it uphill in temperature, and it's also often referred to as a heat pump. A refrigeration cycle, often thought of as a heat pump because you're moving the heat against the direction it naturally wants to go. So here we have QL coming in from a low temperature heat, and through this device we're moving it to a high temperature, QH. That requires work, so we're going to have to put work in to make the heat go against its natural inclination to flow downhill in temperature or make it move uphill in temperature. And to do this we use a working fluid. The working fluid stores the heat and moves it from one place to the other. Let's start with a cold fluid that's part liquid and part vapor, and we'll arrive at how we come up with this fluid later. But let's suppose we have a part liquid, part vapor cold fluid, and we add heat to this cold fluid from a cold space. So we take a low temperature cold space and we'll bring QL in from it and add it to this working fluid. It comes in as a mixture, and the working fluid comes out as a complete vapor, and so we call this an evaporator. We evaporate it the rest of the way. Here it is part vapor here, and here it is all vapor here, so it's evaporated by adding heat from this cold space to this even colder fluid. Obviously the heat has to flow downhill in temperature, so the working fluid has to be even colder than the cold space we're trying to refrigerate. In the standard cycle, we'll say that the standard cycle is where the fluid leaves the evaporator as a saturated vapor, and it contains the QL that we've just added to. To dump that QL to the surroundings now, we have to raise its potential so that now it's hotter than the surroundings. The fluid temperature must be elevated, and we do that with a compressor. So here we have a saturated vapor. We compress it, which raises both its temperature and its pressure, and it usually leaves the compressor as a superheated vapor at a higher pressure and a higher temperature. To do this we have to obviously add work, and this work is the motive force for the whole refrigeration system. A compressor raises the temperature and the pressure of the fluid, and now we can take that heat and dump it to the surroundings with a condenser. So here we have that superheated vapor coming in, high temperature and high pressure, and we can now eject the heat to the surroundings, which will be at a slightly lower temperature than the temperature of the working fluid. So the heat will flow out to the surroundings downhill in temperature as QH. Typically you use a fan and blow air over it, or some other fluid that'll accept the heat from the working fluid. Now as it loses heat, it condenses, so it goes from all vapor to a liquid, and we'll take it out in the standard cycle. We'll call that we'll leave it out as a saturated liquid, so it'll have a quality X equals 0 coming out of the condenser. This is a condenser here. Now, the high pressure and high temperature fluid we have as a liquid, and we pass that through a valve, and if you recall, when you put a saturated liquid into a valve and its pressure drops, it tries to evaporate. We call that flashing. The fluid flashes through the valve, and as it does, it needs energy to evaporate, so its temperature drops, and you may recall that from valve calculations. So we come in as a hot fluid, come out as a cold fluid, at which point it's a saturated mixture part liquid and part vapor. And now we can start the cycle all over again and go back into our evaporator. So here's a diagram of the whole system. We're putting work in. I got that backwards. Work in, and we're compressing it, compressing the saturated vapor. Start here at 0.1 instead. Saturated vapor, superheated vapor coming out of the compressor. That vapor is then cooled and then condensed. Comes out as a liquid here. Goes through the valve, throttling valve at constant enthalpy, you recall, and comes out of the valve as a mixture and then is evaporated the rest of the way. Since it takes energy to evaporate, that's supplied from inside the cold space, or whatever fluid it is, say, that we're trying to cool. Its heat is given up to evaporate this working fluid. Let's take an example. We have a R134 as the R134A, I should say, as the working fluid, and it operates with low and high pressures of 2.8 and 12 bars. Now, on a standard refrigeration cycle, you would see this would be called the suction pressure, and this would be called the discharge pressure. If you look at your car, you'll see an S and a D. If you look at the refrigeration system in your vehicle, you probably see a little S and a D to indicate that those are the low and high pressures. Here we have 2.8 and 12 bars, both of those being above atmospheric pressure, because you normally want, if there a leak develops in the system, you'll want the refrigerant to flow out rather than air to flow in. Air could flow in and carry water and damage your system. So anyway, let's suppose the room temperature is 27 degrees. So we're going to have to reject our heat above 27 degrees. And the inside of the refrigerator will keep it 5 degrees, so our working fluid will have to be evaporating at below 5 degrees C. And let's suppose we have a power input of 0.5 kilowatts, 500 watt compressor, and the compressor has an 80% efficiency compared to, sometimes called adiabatic, sometimes called isentropic efficiency. So compared to isentropic operation, where efficiency is 80% for that compressor. I put together some properties based on this data that was given, and here we have our pressures. Low side pressure 2.8, high side pressure of 12, and I've set up a property process table where we have the quality of our standard cycle, 1 that's leaving the evaporator, and 0, so it's all the way evaporated, and 0 leaving the condenser, all the way condensed here. And from there you can find the following properties. The temperature of the low side, the temperature that you're evaporating at is -1 degree, 1.2 degrees centigrade, and the high side is 46, that you're condensing at is 46 degrees centigrade, well above the surrounding typical surrounding temperature, well above our 25 degree temperature of our room. And so we'll be able to reject that heat here. There's a little diagram of our process. And here we have our compressor. We'll do the calculations. S2 ideal equals S1, and S1 is a saturated vapor, so we'll use SG, and that is 0.9197. Using our knowledge of properties, we find H2 is a function of P2 and S2, and again S2 ideal is the same as S1, and find that H2 is 276. That would be kilojoules per kilogram. And using the same reasoning, we find that T2 ideal coming out of the compressor is 50.9 C. So it's a little bit superheated relative to our condensing temperature, which was about 46. Continuing on now, we have that part filled out. And now we'll calculate the ideal work of the compressor as the delta H. Comes out to 30.1. Now the real work will be higher or lower? Higher, of course, because we're doing work. So we divide by the efficiency and find that the real work is 37.1 kilojoules per kilogram. Plug that back into the energy balance. By now this should be getting fairly familiar. Plug that back into the energy balance and find the actual enthalpy, which is 284, because you added more work, and since you added more work, the enthalpy leaving is higher, the 284. That work went into friction. Which raised the enthalpy up to 284, and of course we'll expect the temperature to be higher also. We find that the entropy as a function of that actual work, H2 real, 284, and the same pressure, the high pressure of 12 bar, the entropy has gone up to 0.9425. And as I mentioned earlier, the temperature is higher leaving the compressor than it would have been from the ideal compressor. We're assuming an adiabatic compressor here. Of course, you could cool the compressor and then it would be lower, but then you've taken entropy out. Continuing on, we have our property process table now filled out all the way through state 3. State from 3 to 4, you see we're going through the valve, and in the valve we have constant enthalpy. So this will be 115.8, and H3 equals H4, and that 115.8, you can either use a chart to find this, which will not be very precise but faster, or you could use the tables and solve for quality, which I've done here to give you a precise answer, and find that the quality leaving the valve was 0.34, 34% vapor. So we're going to evaporate it the rest of the way up to 100%. We can also calculate the entropy here leaving the valve, and it turns out to be 0.4390. Putting all this together, we have, notice our entropies from 1 to 2 is increasing as I go through the compressor. Now we're removing heat in the condenser, so the entropy drops. But as we go through the valve, we're increasing entropy. A valve does nothing but drop the pressure, and you get no work for that loss of potential. And so, of course, the entropy increases. That's a pure dissipative process. Now, if we do our energy balance, the work in is 37.6. The QH rejected to the surroundings 168. QL is 130.7, and notice the work plus the work plus QL equals QH. And then we can calculate our coefficient performance for this refrigerator. COP of cooling is QL. Cooling is the low temperature. Over the work that we put in is 3.48. So for every, let's say, kilojoule of heat that we want to remove, we have to put in, for every 3.48 kilojoules of heat that we remove, we need to do 1 unit of work. Now, if we look at, if you recall, the Carnot COP was a function only of the temperatures, the low and the high temperatures. You recall it's TL over TH minus TL. The best COP we could have gotten from any device we may have constructed would be 12.6. The engineering job is to get as close to 12.6 as we can within the economic and materials limitations of our problem. So we want to raise that if we can, or at least look at where this potential to move 12.6 units of heat with 1 unit of work. Why is this so much lower? So we'll do an irreversibility. Well, first let's scale it up. Since the work, when you're scaling up a process, you look at what you have stated in the problem statement that tells you about the size. We were told that the size of the unit was 0.5 kilowatts. That's the size of our motor, or the size of the power that we're putting into the compressor. If we take that 0.5 kilowatts and divide by the delta H, or the work across the compressor, we find that we can move 0.0133 kilograms per second of refrigerant. Once we know the mass flow of the refrigerant, everything else will scale to that. So we can find the QL, mass flow times the heat per mass, 1.74 kilowatts that we've moved. And so with our ideal process, if we want to compare that to our real process, then the work we would have used, instead of the 0.5 kilowatts, we'll take the QL divided by the COP. Remember, QL over W would be COP, so manipulating that equation around gives us the work for the ideal process to move the same amount of heat would have been 0.138 kilowatts, as opposed to the real work was 0.5 kilowatts. Now we can do the entropy balances and do the irreversibility analysis. And here are the balances. It's out minus in is S generated in each case. And what I'd encourage you to do is to do your balances and confirm that these are the entropy generated terms for each of these units. And this is for the real process. So what we've done is looked at some refrigeration calculations. We've done the compressor, isentropic compressor. We've looked at the isenthalpic valve. Again, I say isentropic compressor, or the efficiency. First you do isentropic if you're going forward through the problem. You're given an efficiency, and then you apply the efficiency to the ideal work to find the real work, like we've done here. And we've looked at exchangers, which are isobaric. We've assumed they're approximately constant pressure, or neglected any pressure drop. We've looked at the real versus the ideal, the actual coefficient of performance, the ideal coefficient of performance, and now we need to explain the difference. On scale up, we took a basis of 1 kilogram, which I typically do for cycle problems. I'll look at the whole cycle as far as I can with the basis of 1 unit of mass, and then use the known load. In this case it was the load we had was work of the compressor. You may be given, instead of work, you may be given the amount of heat that you want to move somewhere, but at any rate you'll use a known load to calculate the mass flow, and then scale the other loads according to that mass flow. So for homework, I'd like you to do is calculate the irreversibility from each piece of equipment. We started doing it, put up the balances. You just have to plug in the numbers and go through and account for the difference. We did this with the Rankine cycle. I want you to do it with the refrigeration cycle. Account for the difference between the ideal cycle work and the real cycle work, which was higher, 0.5 kilowatts. You should be able to find all those differences exactly. And then I want you to look at Chapter 11 and work problems 12, 14, 17, and 21. And this actually concludes our section on pure component thermodynamics. From here on out we'll be looking at mixtures, and we'll get into air conditioning and water and air sorts of problems. So that'll do it.